Hari Om children, good morning to one and all. Today we are going to discuss about how to draw the graph of a LPP for a bounded region. How to find out the feasible solution from the graph for a bounded region. So before entering into today's session, let me just recapitulate what is the main objective of formulation of a LPP. We all know that the key terms involved under the formulation of LPP is LPP, a linear programming problem. It is having three aspects. So which are the three aspects? As discussed earlier, the three aspects are, the first one is we need to optimize the given linear function, which is known as the objective function of the linear programming problem, subject to certain conditions. So which are the conditions? The conditions are, one is the linear constraints, or it is also called as linear inequalities, which is represented here as Li. And the other one, another condition for formulating a LPP is, it is the non-negative restrictions or the non-negative variables included in the objective function. So let us move on to the graphical solution for a bounded region in a LPP. So let us take this particular question. Here it is given that solve the linear programming problem. And what is the problem given here? Maximize. So the optimizing concept will be either it is maximize or it is minimize. So here the objective function is maximize z is equal to 4x plus y. This is the objective function. As I mentioned, this is the objective function subject to the constraints. What are the constraints which is given in red here? What are the constraints here? X plus y less than or equal to 50, 3x plus y less than or equal to 90, and x greater than or equal to 0, y greater than or equal to 0. So let us learn how we are going to draw the graph of this particular linear inequalities and how are we going to find out the optimal value for this particular objective function graphically. Let us move on to the graph. Yes, so as discussed, let us solve this LPP graphically. So here I'm going to solve this LPP graphically using the GeoGebra tool. I'm going to use the GeoGebra tool here to solve this particular LPP. So let us move on to the solving of this particular LPP graphically. So for that, we know that we need to maximize the optimal function. So here the optimal function is already given. Now I'm going to draw the graph of the constraints. So let me draw the graph of the constraints. So for that, the first constraint is x plus y less than or equal to 50. So I'm going to draw the graph of x plus y less than or equal to 50. So x plus 5 less than or equal to 50 is one of my constraint, linear constraint or linear inequation. And what is the next linear inequation given in the question? The next linear inequation given in the question is 3x plus y less than or equal to 90. 3x plus y less than or equal to 90. So these are the linear inequations. So we need to draw the graph for these linear inequations. And after that, you need to mention the non-negative restrictions also. What are the non-negative restrictions? X greater than or equal to 0 and y greater than or equal to 0. Now let us observe the graph. Let us see how the graph of this particular function is. So from this, we all will be getting a fair idea about the nature of the graph. Now when we see this, from this we'll be able to identify the region. You can see here a region, a closed region here. Probably it is a quadrilateral. So this this closed region is a bounded region of the given LPP. After getting the region, after identifying the region, then we are to find out the corner points. So which are the corner points here from this particular graph? The corner points are, one is, you can see my cursor, one is the origin 0, 0. The next one is, what is the next point? What is the next point? It is 0, 50. And what is the another point? 20, 30. And the last one is what? 30, 0. So these are the corner points of that particular bounded region. These are the corner points for that particular region. Once we identify the corner points, then we need to substitute these values in the objective function. So let us substitute these values in the objective function, and then we'll find out the optimal solution. So again, I'm repeating, what we should do in the formulation of a LPP is we need to draw the graph of the inequations along with the non-negative restrictions. This is what we need to do here. Yes, so after drawing the graph of the particular LPP, yes, we need to substitute the corner points or the feasible solution in the objective function. So these are the corner points or the feasible solution in as per the graph of the given LPP. So one of the corner point is 0, 0. So when we substitute 0, 0 in this particular objective function, what is the objective function here? The objective function is z is equal to 4x plus y. So when we substitute the particular corner point 0, 0 in this objective function, we will get the answer as 0. Now we are going to substitute 30, 0 in this objective function. So we will be getting 120. And then we need to substitute the point 20, 30 in the objective function 4x plus y. So the answer will be 110. And we'll be substituting 0, 50 in the objective function z is equal to 4x plus y, and the answer will be 50. Now we need to observe these values 0, 120, 150, 0, 120, 110 and 50. From this, it's very clear that the maximum value is what? The maximum value is 120. So the maximum value for the given LPP, what is the maximum value for the given LPP? It is 120. So this is the working rule to solve a LPP graphically. Let me recapitulate the concept of finding out the optimal value of a LPP graphically. That is, the first step involved is draw the graph of the inequations and also the non-negative constraints or also the variables included in that particular LPP. After drawing the graph, fix the corner point through which we'll be able to identify